Good morning to Dr. Nazri and fellow friends. My name is Benjamin Elvis, and today I will be presenting our project, which is Simulation and Performance Analysis of a Thermal Energy System using Aspen ICs, a component level study on pump, cooler, turbine, and heater operation. This project was completed in collaboration with my teammates, which is Akmar Danish 103165, Shafiq Afzan 102766, and myself Benjamin Elvis 103529. These abstracts give an overview of the simulation. In this project, we use Aspen HYSYS to analyze four major components, which is the pump, cooler, turbine, and heater. For example, the pump increased pressure from 2200 kilopascal to 10,000 kilopascal, requiring about 362.7 kilowatt of power. The cooler reduced temperature drastically from 45.81 degrees Celsius to negative 30 degrees Celsius with a huge cooling duty. The turbine expanded the fluid and generated a significant amount of energy, while heater raised the temperature from 31.19 degrees Celsius to 330 degrees Celsius. Overall, this simulation gave us important data about energy use, recovery, and system efficiency, insight that can help improve real industrial operation. Here is the table of content for our presentation. We will begin with the introduction, then outline the aim and objective for the project. Next, we will go through methodology, result and discussion, and finally the conclusion. A bibliography is included at the end for the reference. Let me begin the introduction. Thermal and mechanical energy management is a crucial part of industrial operations, especially in systems like Rankine cycle used in power generation. In our project, we simulate the thermodynamic behavior of four essential components, which is pump, cooler, turbine, and heater, using Aspen HYSYS software. These components are commonly found in modern thermal systems. We focus on key engineering challenges like pressure drops, heat transfer limit, and energy losses. Our goal is to gain deeper insight into energy efficiency and process integration, especially relevant to industrial development in Sarawak.
Aim and objective of our project is to simulate the system in Aspen HYSYS using the Peng-Robinson fluid package to perform detailed mass and energy balance calculation, including energy destruction, to identify optimization strategies such as heat integration and enhanced turbine recovery, to validate key assumptions such as efficiency, fuel source, and negligible pipe loss. And lastly, to ensure the model supports scalable energy solution aligned with Sarawak's industrial sustainability goals. So moving to methodology, the simulation was done using Aspen HYSYS version 12.1 under steady state condition. We use the Peng-Robinson equation of state to predict the fluid behavior accurately. The system includes four main components, which is first, a pump that increase pressure from 2200 to 10,000 kilopascal. Second, a cooler that lower the temperature from 45.81 to minus 30 degrees Celsius. Third, a turbine that expands the fluid from 10,000 to minus 100 kilopascal. And lastly, a heater that raised the temperature from 31.19 to 330 degrees Celsius. We perform a mass and energy balance calculation, an energy analysis, and identify ways to improve thermal efficiency. Some assumptions were made, such as steady state operation, negligible heat loss, and fixed fluid properties.
In this simulation, demonstrate the operation of pump, cooler, and turbine in chemical process. The pump increase fluid pressure, the cooler reduce fluid temperature, and the turbine generate energy by reducing the fluid pressure and temperature. The pump elevate the pressure from 2200 kilopascal to 10,000 kilopascal, resulting the pressure change of 9800 kilopascal. The required shaft power was calculated as 362.7 kilowatt with a constant molar flow rate of 5196 kilogram per mole. This aligns with typical value observed in industrial feed water pump. Cooler reduced the process stream temperature from 45.81 Celsius to negative 3000 Celsius, removing the approximately 1844 kilojoule of heat. This large cooling duty highlight the importance of thermal management, cryogenic and liquefaction related applications. Last but not least, the turbine expanded the high pressure fluid from 10,000 kilopascal to 100 kilopascal, producing 7,393 kilojoule per hour of chemical energy. The negative outlet pressure implies vacuum level operations typical in high efficiency power system and demonstrate significant energy recovery potential. Heater component, the heating unit increase the stream temperature from 31.19 Celsius to 330 Celsius with heating duty of 2.567 kilojoule per hour, stimulating the high temperature heat exchanger or boiler.
To conclude our presentation, this simulation gave us valuable insight into how each component of a thermal energy system performs. We observed the pump increase pressure efficiently, the cooler handled large-scale heat removal, the turbine recovered mechanical energy effectively, and the heater raised temperatures to meet industrial heat requirements. More importantly, the project helped us understand the importance of energy balance, component efficiency, and potential areas for optimization in system design. For an application point of view, this study supports the development of efficient and scalable energy systems, especially for use in industrial zones such as those in Sarawak, where sustainable and low-emission technologies are becoming increasingly important. That's all from our group. Thank you.